So in this video we will study the particles in general, and to do this you should, as before, you should have seen the previous videos to get an attention understanding of what this is all about. Okay, so the particles, we know that we have that particles in general, they obey the law of that the energy is equal to the total mass times c squared, as you can see in this equation. And this is true for electrons and positrons, but it's not true for photons and neutrinos. They are independent of the velocity and they don't have a gamma factor. So it follows that you can exclude photons and neutrinos. They don't make a part of the particles. The electrons and positrons are really the only configuration that is created by the DAONs directly, which could be involved in the construction of the particles. So we start by studying, continue the studying of electrons and positrons. Earlier we have looked into the condition, the characteristics in interaction at a certain distance away, so that the reference radius of the electron is constant. So this is well documented as in earlier videos. Now we will close in to very short distances. So this reference radius is not anymore constant, it's modified, and it changed quite a lot of things. So we cannot anymore just make some analytical reasoning, but we have to make a simulation program, which was done. It's called PART. It's a three-dimensional, so it's really a sphere with electric field lines, potential surfaces, etc. Of course, in the source of the DAON theory. So we made a sphere with 120 points, and we make many such spheres at different radius, and then we draw radial lines through these some different spheres, and then we use the DAON theory to see how this is modified when you come in close contact. You get the field lines is always in the direction of the medium direction of the rotational axis of the DAONs, and the potential surface is always perpendicular to the rotational axis of the DAONs. This is quite a simple and classical approach. The program part has no parameters. That is to say, you place them manually, let's say, or by introduction. You put the particles in certain position, and then you calculate the variation of the force potential of each particle using this kind of mesh. So this is a bit it's not very nice, let's say, but it can be done, especially for symmetric particles, which we will see later on. The main particles, in fact, are quite symmetric, so it's not so difficult to do it yet. Okay, one main problem with these particles is that if electron and positron comes very close together, they start to deform strongly. They're not in a sphere anymore, but they are pressed or some sense. And this leads to that the DAONs in each shell doesn't anymore have the same size. They have a variable size. And as we have already seen earlier, that means that you have to take the geometrical mean of the radius of all the particles in a shell. You see here the interaction between two DAONs comes out like this. And you can then, if you look to a whole shell, then you have to multiply all the DAON radius together and make the geometrical mean and arithmetical mean. You divide the geometric with the arithmetical mean, and then you get a constant, which you say how much the shell has been contracted in that specific interaction. The fact that the shell is contracted, becomes smaller, leads to an increase in force, which has to be compensated by a decrease of the order. so that the radial equilibrium is always constant. But since shells become smaller, this is you have many shells on top of each other, which means that you have to add new shells all the time, so that the mass is going up. So when you start to deform a shell of an electron or positron, then the mass goes up automatically. It never goes down. I mean, the mass is minimum when you have a perfect sphere. Then any deformation you do, the mass starts to go up. Okay, so if you look to one shell, then the contraction is quite small. But since there are often many shells, or thousands of shells, then the contraction at the end becomes quite big in the center of the electron. So the mass can be growing to quite high values. So, okay. So we're using this part program. You cannot. It's not a dynamic program, but you have to place the particles in certain positions, and then calculate. You can then calculate the deformation of the shells and the variation of the characteristics. So this is a bit of work, but as far as particles are symmetric, this is not so difficult. So this can be made. In fact, it has been made. So we will start with the interaction of the two electrons. And you see here in this figure, here you see one shell as representative, and then you have the electric field lines coming out interacting that you see here. Okay, then you can obtain some of the values from the interaction. You displace the electrons so they come closer and closer together, and you take the points of the interaction. So we compare this with the classical values of the force and mass, essentially. As you see here, this is the definition of the classical values. Now, in this representation of the diagram you see here, you have a logarithmic shell on both sides, because otherwise then the variation of these values becomes very important. So to see the whole setup of data, you have to present it in a logarithmic manner. So you should be aware of this. This can be tricky, so you have to be careful when you look at these graphs. So we start quite far away from the one from the other at around 10 Fermi, so it's quite far away. And that distance and also the classical values are comparable with the DAON theory values. You see that they start off from the same points, more or less, the mass and the force. You have also the contraction, but the contraction really follows the mass variation. So I will take away the contraction, disappears later on. We just look at the force and the mass of the particles involved. So here you see classical mass versus DAON theory mass, and force the same thing. You see that this is they come start from the same point. You have a small decrease of the force, the down calculated force, due to the reduction of the reference radius and also the smaller number of shells when you're coming closer to the center. So you have following the classical values, and then it goes down slightly. The mass is more complicated. I mean, here you have the mass first is going up and then it goes down. If you close in to, I mean, you have the increase is due to the typical electrostatic relation, which makes the mass goes up. And then when you come close, then you have much fewer shells close to the center, so the mass goes down. So this is quite simple. It's nothing very strong. There is no strong variations really in this kind of thing. So you can, I can present to you some calculations here. I mean, this is the force calculation. You have to sum up all the external electric fields into some factor OT, I call this, and then you have the force T, which is some sort of enhancement factor, let's say. Well, okay, so well, so next step we put an electron and a positron, and we come closer and closer to see what happens. As you see in this figure, now you have the same thing. You have one shell, a representative shell, just to see how this is made, and you have electric field lines, which is now, as you see, completely different than from the electron-electron interaction. Again, you have the diagram which is shows here. You see there is if you look to the mass, you see the mass starts out from about the same value in the classical case, and then you cut the classical case when you come as close as classical electron radius. Afterwards has not too much sense. Okay, so you see here what you should notice is that the mass goes up very high at some 1 fermion distance between the electron and the positons. You have extremely high values of the force and the mass. Oh, not sorry, of the mass, not the force, of the mass. And this is interesting because this could be the explanation for the particles. I mean, electron and positron interact very strongly, and you get a strong enhancement of the mass. So this is the main point. So you see that they follow more or less the classical case at a certain in the beginning, and then when you come close to the one to another, you start to get a growth of the mass very quick, and this has a strong interaction. Okay, so you show here how you calculate the mass of one electron positron. So it's an integral. I will not go too much into this. You should look into the book. There is a book here of you just take the Google and say the DAON Theory book, and you have indication where you can find this. So it's been very difficult in the video to explain mathematics really. You have to have a drawing board or whatever. So I will just tell you how it is, and then if you have a real interest in mathematics and details, then you should buy the book. Or you can eventually find an ebook on the internet, maybe. Okay, so we have the same thing as for the electron. We have electron positron now, and we will have a look at the annihilation, which is of importance, as you will see later on. Now, in annihilation, what happens is that an electron and a positron comes close together. They decay into two photons. So this is a typical reaction. So we will have a look at this. You can see the figure. You have in this figure you can see that how they are directed, the downs, the axis of the mean axis of the downs are corrected inside and outside of the two electron positrons. So if you have a closer look at the lower figure, you see that this results in a separation in three different regions. You have the regions between the two electron positrons. You have the downs pointing in one direction, and the external part of this interaction you have downs pointing in the same direction, but the opposite to the central part. So this gives you three regions essentially, and external regions. Once you have created, let's see, three quasi photon, let's say, then if you have some speed or something, they will be displaced one relative to the other, and then the two external parts will rejoin each other and create one photon. And now if you look to the direction of rotation to an electron and photon, when they come close to each other like this, then one is turning in the left-handed sense and the other in the right-handed sense. So when they encounter, they have the same direction of rotation, so they are not don't have interaction in the sense, transport sense, let's say. So they create this thing when they comes a bit away from each other, and you have two photons. Then they are parallel to each other more or less, and then they according to the direction of the photons, they repulse. They have a repulsive force between them, so they will leave the interaction in opposite direction. Two photons with very closely the same number of downs, so they have the same energy, same mass, going away one from the other like this. This is a scenario of annihilation, and this is what you find in a dedicated experiment. So now let's continue, have a look at the muon. Now if you have a muon, you can first of all look to the decay of muon. You see a muon decays into an electron and at least one or several neutrinos. So so this is a very, very simple structure, and according to the DAON theory, this should be simply an electron, for instance, with two positrons, or the opposite, one positron and two electrons around it. This should be aligned one with the other due to the electrostatic interaction. So this is quite straightforward, and you see the geometry of the muon as it is simulated here. So what's it? You can see this, and you can move them closer to each other, and that is what you see in the graph here. So here we have taken away the contraction, which is just follow the mass. It's not very interesting to look at. So we have the electron. It's a external part. Electrons are placed around a central positron. So we have the electron, the positron, and the force. So the force is quite not very strong. I mean, it's the smallest, lowest graph here, and then you have the electron and the positron. The positron, which is in the center, has the strongest mass, and the electrons around it has somewhat smaller mass. So you can then play around with this a bit. And what happens now here is that this muon has, when it's well symmetric, it will be quite stable. But you can see that the central positron will be in contact with one or the other, and finally it will be an annihilation with one of the electrons. And this is then creating, that's before the annihilation, it's the same thing. You have three area of quasi-photons, and the one of these photons will be absorbed by the electron, which on one extremity, while the other will be rejected in the opposite direction. It follows when you have two photons and coming, since they are pushing in the opposite in direction as earlier. It's not. It's in the line of the central part of the electron positron. So you have this line, and the two photons will be pushed one to the other, towards the other, and then that means that they will slide one past the other, and they will be parallel more or less with opposite directions. And this is really a real invitation to create a neutrino. And since now the photon's energy is different, it's not as symmetric anymore, but quite asymmetric. So you have some excessive downs order on one side, too many downs. So you you could have a supplementary creation of another neutrino or something like that, or photon or neutrino. So this is the decay of the muon. You have an annihilation, and one electron absorbs some energy, some photon, and the rest will be created to make neutrinos, certainly, and maybe a photon or a photon and a neutrino together with this. Yes, it should be said that, of course, since we just place the particles in their position and then we calculate what happened, it means that we do not calculate in the dynamic process. That, I mean, we don't include the velocity of the participants or something like this. This is really static. What is interesting in this is not to know exactly the result of a collision or something like that, but it's to see on the graph what is if we can find some stability. To have a particle, there must be some region of stability in the graphs, and that is the main purpose of this program, is to find where are the stability region and what is the mass and force, etc. at this region. So when you get the correct mass of the muon, we have that the distance between the positron in the center and the electron outside is 0.16 fermion, so it's quite small. Okay, we should say that we have 120 points in the azimuthal sense, and this is insufficient really. You have quite a big error bars. It's basically if you jump from, if you have, let's say, 50 points included in some surface, instead of 49 or 51, you can have, gives quite big errors, and so this is what you see also in the graph. It's not very smooth, it's jumping around a bit. So we have something, it could be from, well, let us say 10 to 20% error, or something like that. So then, if you take any particles, of course, you have the number of electron positrons inside. You just sum up their radial equilibrium, and at some distance away from the particle, you will have an integral value, positive or negative, which is the sum of all the radial equilibrium. So the charge is always integral, and this is what you normally find in particles. So this is very simple presentation of the muon. And this is we will use this to understand the strong force. Of course, strong force you don't really believe to have in the muon, but the muon in fact is kept together with the strong force. We will explain how this works. You will have the same effect in all particles we will study here. It's the strong force. It's like parts of any particle which is kept together in some way. We take the position where the distance between the particles are quite high, so on the far away, let's say the particles are, the electron positrons are far away from each other. And in this region of the graph you see that if for instance, let's say we take an electron, if the electron has too high mass compared to the graph values, then this is the fact that he has too high mass. It means too high number of downs, which means that he has a weaker attraction force relative to the graph. So it means that he will move in principle versus bigger radius, but a bigger radius, the mass goes down, a bigger distance between particles. So if he moves outwards, the mass goes down, which means that his mass, which was already too high, will be even higher than before. And if you take the same thing and you say it has too low mass, then a low mass gives that he wants more mass, so he gets attraction. So he wants to take downs from the surrounding particles or fields or whatever, which means that he's increased the force and he goes to the shorter distance between particles. And this will lead to a further, it's even smaller value of mass compared to the graph. So this is an instability. You have some sort of saddle point, let's say, and you are sliding down or up, and you decay or you slide over maybe on the other part of the graph. In any case, this is not a stable place, so you can say that the external part of this graph, where bigger distance between the particles is unstable. So now we will have a look at the other part of the graph, and there you have the opposite situation. So you have, since the graph is growing, so if you have too much mass, then you will have a reduction of the force between the particles, which means that you will slide upwards on this graph, which then gives a better fit for the mass for your mass which was too high. So when you go up, you come into the correct region of mass. And the same thing, if you have too little mass, then you will move, it is stronger attraction, so we'll go to the left side, we'll slide down the graph, so that your the relation of mass and the graph values, which is the optimal mass, will come closer together, and so this gives stability. So you have the stability in that part of the graph. So to be more exact, what will happen is that you have a particle moving up this graph here, and he will move until he finds a position where the force to push him closer or further away are equally strong on both sides of the electron. The electron is not a point particle, but it's some extension, so you have a difference. And when you find this position, then you are in a stable position. Okay, so this is the stability point. So this smaller line you see on the graph, that indicates the position, more or less, of this stability point. As I told you, we have some error bars, so it's not very precise, but in any case, it's close to the correct value of the particles in all cases, in fact. So this is quite good. Okay, as you see, then this a variation of the force, let's say, this is a second derivative of the graph, should be 0 to this point, so that you have the same gradient on both sides of the particle. Okay, so what happens here? You see that this, the values of the force keeping this stability area together, let's say, it's in fact very strong. And if you examine, in case of the muon, you get something around 1000 Newton per Fermi. This is a very strong gradient to keep the particles in position. But even if this is a strong thing to keep them together, you can still not stop the annihilation, because you have strong attraction between positron and electron, and it will end up with an annihilation of the muon constituents. Okay. So after this, we continue with the P0. The P0, of course, since it's 0, it has to have the same number of electrons as positrons. And if you look to the decay modes of the P0, what you have here, then you see that the most likely geometry of this is 4 particles, so 2 electrons and 2 positrons, placed in a regular manner, so that the electrostatic becomes 0 and you have some stability. And again, you have this graph here. Since it's the same distance for electron and positron, so I have the same characteristics, so it's just one graph. You have, or two lines, you have a mass and force of each participant. And this is quite simple. Since it's very symmetric, you have a nice curve there. And you get the same way as for the muon. On the smaller part of the rising gradient of the graph, you have a stability point, which is indicated here. And so you have a distance from the center around 0.2 Fermi for all participants. And the strong force is here around 10,000 Newton per Fermi, so it's even stronger than before. But in the same way as the muon, or even worse in this case, you have that they are really attracted to each other. You have a very strong annihilation almost immediately, so it's very unstable. As you see in the decay mode, you can even have a separation of all the electrons, positrons from each other, or you create an annihilation with some gamma or whatever, 2 gamma. Okay, so this is not very just to see the image how it's done here. So now we continue to P minus. So P minus, again, if you look to the decay mode, you see it comes out mu minus with some neutrino or gamma or whatever, and the P minus to mu minus. So if you expect that this is very simple particle, so it should be a decay again of interaction between electron and positrons. So you add 1 electron and 1 positron, and you obtain the following structure that you see here. So this is for the P minus. You have 3 electrons placed electrostatically in triangle, and then you have the 2 positrons which are seeing each other through the center of the triangle. So you have, and this gives a symmetric position. So this is okay. So here you get that the electrons are 0.25 Fermi from the center of symmetry, 14 MeV of mass, and the positron has 0.147 Fermi and 50 MeV mass. Strong force, again, it's around 10,000 Newton per Fermi. And again, this is very unstable. I mean, again, you can have annihilation very easily, that one electron comes close to positron, and you decay, and you then have 3 rest. You have 2 electrons and 1 positron remaining, which make a muon. And this decay very quickly, as all mesons, besides the muon, which is a bit more stable because it's quite simple, I think, in the geometry. It's a bit more stable. Okay, so this, you see that this, if you now go to higher mass mesons, they are most likely made up by a combination of pions, muons, or whatever, to couple them together. And so they're all decaying very rapidly in the same way as the individual particle. So it's not much to say. This construction, you have to, it become more complicated, of course, the construction if there are more particles. But they decay very quickly, and you can calculate them in the same way as was already done here. But you have to have some better computer, because it takes time to make this type of calculations. And you have to have a quick, a bigger computer, more powerful, and maybe some program which can move automatically the particles in the correct position, etc. So this is just, let's say, a taste of what is particles and how you can work with them. Okay, so the next step now is the proton. So we have a look at the proton. Again, the proton has to be made up by electrons and positrons. All baryons, in principle, all particles should be made in the same way. So what is this is extremely stable proton, so it must have some specific geometry, and also it has must have a higher number of electron and positrons because it has much higher mass. So we will have something which is a higher number of positron electrons, and it has to be a very symmetric structure to explain the stability. So thinking about that, I was considering molecules or atoms in about the same size, but with opposite signs, which you have, for instance, in the salt of different kind, CaCl, for instance, and water. Okay, and in this case, you have that the positioning in the crystal that we know. They create a sort of cubes, which is when the positive cube, which has an eight positive particles, and then you have the negative cube, if you move the corner of one of the cubes into the center of the other cube, then you get a specific geometry, which is interesting because it's highly symmetric. In the case of the proton, I was looking to something that was symmetric of this type, and the most simple as possible. To have stability, it's always easier to be small. I mean, it should be as simple as possible and absolute symmetric. And I found one possible symmetry, which I've tested, and it looks correct. So you have a cube of the points of the corners are a position of the positrons, and then you have the electrons placed a bit outside the surface of each side of the cube, and one electron is in the center of the positron cube. So this gives you the following geometry, as you see in this figure here. The central electron is of course placed extremely symmetric in the middle of the proton, and this gives specific characteristic because since it is very symmetric in the center of the proton, the deformation of this electron is very small, leading to a very small mass. It's about the same as a normal electron mass in order size, and the difference is this is very, very small in the center. The mass, not the force. The force is equally strong, more or less, as the other. The electron and positron, which are in the outer part, has a much bigger mass. They are deformed, strongly deformed, so they have strong masses. And this gives a very strong particle. So we have the positron, which should be around 0.33 Fermi from the central electron, and the electron slightly smaller, than 0.325 Fermi. The mass are around 55 MeV for the positron and 80 MeV for the electrons. And the central mass is around 0.5 MeV, so it's not, as you see, it's very, very symmetric. Okay, so you see then this symmetry. The part of the proton mesh you see here is really, as there are many particles, so it's a bit messy, but I mean you can see the idea. Okay, so we get here the graph. So I put in the electron, central electron, but it's very weak, of course. Then you have the force masses of the electron and the positrons. They are in this graph very close together. This is the masses go up, or the forces, I mean, they are very close together. So it's almost perfectly the same. Okay, so here again we have indicated where you have the approximate position of stability, and this corresponds more or less to the mass of the proton. Okay, as you should notice here that in this approach we have, in case of the mesons, we have two types of particles, electrons and positrons, with the same value, same characteristics. And you have, in the case of the proton, you have three different particles. You have the electron and the positron in the external part, and the central electron. So you have three types of particles in the baryons. And this aligns with the number of quarks proposed by the standard model. So I think in the experiment they do on this, you can see that there are three types of interaction in the case of the proton, but three types of reaction doesn't mean that there are three particles. It means that there are three types of particles, where each type could have a different number of participants. So this agrees in some sort with the experimental results, of course. And the standard model, well, we will not be too, we will not make any bad comments on that. Well, okay, so let's continue to the neutron. The neutron is just a proton, and you add an electron to it. You see the neutron has a mass which is slightly higher than the proton. Now if you have a positive and a negative charge closing in towards each other, you have a reduction of the force due to the potential differences. But when you come very close, then you should have a growth of the mass of the proton and the electron, and this is what you could expect. Now, so when you come close together, then you have that the action from the proton becomes quite strong, but the electron is now very close to the proton, so that he cannot, there is no place to make any associated wave of the electron or something like this, and this is the difference between the hydrogen atom and the neutron, is that the electron cannot have an associated wave. There is no room for that, and it's also, he is so close that he can see the individual particles of the protons, which means that he will have a very shaky path, and this is not possible for him to make any associated wave. So there is no place for an electron within the proton, so the electron has to be close to the proton but not inside it. And also we can say that the electron should be quite close to the electron, so close that you should have some beginning of an enhancement of the mass. That's why the neutron has a slightly higher mass than the proton. So you can say that the electron should be around some, let's say 6-7 Fermi from the proton, something like that. Okay. So what we did now, we put the electron just in front of the corner of the positron cube, so that they have just see directly each other, the electron and the positron of the proton, and then we close in with the electron, and we see the variation of the mass of the proton, because the electron, in fact, the mass of the electron changed very little, so we don't even put it in, we just look at the force and the proton mass. And as you see on this graph, this again we see that there is irregularities, which is due to the scarcity of the mesh. But if you come, you see that it is varying quite strongly, but when you come close together, then this variation is reduced, because the points of interaction becomes denser, so you have less variation at the small radius. So this tip you see here that goes up and then it's tipped in on this graph. That is probably with quite a good security. Okay, it seems like this should be correct. So it means that when your electron comes close enough to the proton, it falls into this trap of potential, and that is why the neutron is almost stable. Of course, the proton or the electron is moving around. It's moving around in around the proton, so he sees. Locally sees the positrons and the electrons, and he will have a very erratic path around this proton. You can make a lot of different things. So you can imagine that when he passes just in front of a proton, he has some probability to be thrown out, which gives the decay mode for a neutron. If you look to the heavier baryons, they should be made up by a proton or maybe several protons with some meson, p meson, muon, etc. attached to it. And so this is not very much to say about that. The nuclear force, yeah. The nuclear force is simple. When you have a nucleus in an atom, for instance, when you have some particles coming close to the nucleus, then, as I told you before, we have a strong variation of the mass gradient when you come too close. So your particles coming in too close to the nucleus will be attracted toward the nucleus, and this is much stronger than the charge electrostatic force, so this is neglectable. You have always, for any particle besides the photon and the neutrino. The photon and the neutrino just rearrange their down structure, and they don't change the mass. But the electron and positron, yes, they will be deformed, and they want to have more mass, and so the mass will grow if they have access to something, field or other particles to extract the downs. So this is why you have the nuclear force. You can When they come close, like a couple of Fermis away from the neutron and the nucleus, then they are attracted strongly towards the neutrons. The same thing of the protons and the electrons within the nucleus of an atom. They are very strongly attracted to one another, and they create some sort of equilibrium. You have also the protons and the electrons, which are attracted towards the nodes where you have strong positive fields, of course, and you have some specific geometry of the protons and the electrons inside a nucleus. This is not. I'm not trying to study this because the computing time becomes too long, but this can be done in a powerful computer, of course. When you have in such a close packed nucleus, of course, you have also interaction where it depends on the geometry of the baryons, that is of the protons, that is the position, the exact position of the positron and the electron relative to another protons. We have some specific geometry which has to be developed. Okay, so I will stop there, nuclear force. Then we go to the weak force. What is the weak force? Well, we have seen here that the weak force seems to be just annihilation between electrons and positrons, and maybe some other reactions which is clearly not the nuclear force. So this is very it's not easy to define the weak force. It's the force which is not the strong force, let's say, and annihilations, etc. What about the heavier bosons and W2 ATX, etc.? Well, in the DAON theory, they don't exist. Quarks, gluons don't exist. That doesn't make any sense. But of course, you can play around with the mathematics and to do something with the quarks and gluons. And of course, the particle physicists will not like the idea that it's made up of electrons and positrons. So I don't expect a welcome from. We should make some comment on the stability of the proton, which is very important. So first, let us see the slope of the graph of stability, as you see here, the mass graph relative to the distance. In the case of the muon, we had about 1000 Newton per Fermi, and the P0 and P minus meson had around 10,000 Newton per Fermi, while the proton has something like 100,000 Newton per Fermi, so it's getting stronger and stronger. We should maybe say that the fact that the muon has a lowest variation of the mass, just 1000 Newton per Fermi, probably is one of the reasons why his decaying time is longer than for the mesons. So in this same way of thought, you should say, well, the proton then must be decaying much faster than the meson, but it doesn't. So why is it the case? Well, if you look to the proton geometry, you find that the geometry of the photon is extremely symmetric, which means that if you move one of the electrons external, especially external electron positrons, if you move them in any direction, the variation of their mass will be such that they are pushed back to their original position with a very strong gradient. So this is the reason for the stability of the proton. The central electron, it has very low force in it, so this is, but it has some electromagnetic force, more or less, compared to the external, in reaction to the external electrons and positrons. If we look at the central electron, we find that this is very symmetric, so its mass is very low, and it doesn't play a very big role in, if we move this around, you don't have a strong force acting on the central electron. But if you look to the effect that the movement of the electron has on the external positrons and electrons, then you will get an asymmetry between one side and the other side, but still, so that the external electrons and positrons will react in a way to close in. They will move with the central electron, let's say. So the central electron also cannot move around freely. It's really blocked in the center, even if the forces involved are weaker.